Hello and welcome to Earthquake Tip number 31. My name is Shailesh Kumar Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces to 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to comprehend language to our professionals who are in the field designing and constructing structures, especially our architects and engineers. But before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. This earthquake tip number 31 is on why do buildings sink into the ground during earthquakes. There have been several instances of ground failure during earthquake causing damages in the structures over them, and through this tip we will try to understand the possible ground failures. The most common phenomena is liquefaction of soils. Let's understand what is liquefaction of soils. During earthquake shaking in sandy, that is cohesionless soils that are loose and saturated with water, a special situation called liquefaction arises during earthquake shaking. As you can see in this figure 1a, horizontal shaking of earth at the bedrock level is transmitted upwards to overlying layers of soil. Saturated, loose cohesionless soils have voids between soil particles which are filled with water. During strong earthquake shaking, loose sand tends to densify. That means it tends to compress water. But water being incompressible, that is, water tends to escape out. However, water cannot drain quickly from the soil and therefore pore water pressure increases in soil. This reduces the effective stress between soil particles. At some stage, the effective stress may become almost zero. In that situation, since soil strength depends upon this effective stress, the soil may lose its shear strength completely and behave like a liquid. This phenomena is called liquefaction and is explained in this figure 1a. Buildings and structures rested on such soils topple and sink into the ground, as you can see in this figure 1b, which shows collapse of buildings during 1964 Niigata earthquake of Japan. Now let's look at this figure number 2, which shows that depending upon soil properties and ground motion characteristics, the earthquake may impose shear stress demand in soil at some depth that exceeds the shear capacity of soil. This helps in soil liquefaction over this depth where demand is exceeded from the capacity, as you can see in this figure 2 with red color. Now let's understand the physical consequences of liquefaction. During liquefaction, as explained just now, cohesionless soil water mixture tends to behave like a liquid and hence the ground tends to flatten out. For example, embankment may collapse while the depth of ponds may reduce. This can also have serious detrimental effects on structures which are being explained to you through these figures. First is sinking and uplifting of structures. As the cohesionless soil water mixture liquefies, structure tend to settle or sink into the ground. In many cases, some part of the building may sink and more than the other, leading to tilting of buildings, as you can see in this figure 3a. Similarly, buried structures tend to uplift and float up to the surface because their overall density is lower than liquefied soil. See this figure 3b. The next consequence could be shear failure of slopes and lateral spreading. As you can see in this figure 4a, when the soil at a lower level loses its strength to hold any load, the overlying soil layers may slide laterally, especially when the slope is steep, that is more than 5%, and the original soil is loose. This can cause landslides extending over hundreds of kilometers of motion of soil mass. In both loose and dense soil, where the slope is gentle, that is less than 3%, forward movement of large soil mass can cause disintegration of the large soil mass behind it, as shown in this figure 4b, and it is called lateral spreading. Therefore, the structures may sink and destabilize if supported by such soil. Further soil movement due to lateral spreading can exert significant stresses and damage in foundation and bridge amendments causing damages. Having understood liquefaction and its physical consequences, let's see the parameters which influence liquefaction. Vulnerability of a site to liquefaction depends on these factors as shown here: soil properties, earthquake shaking characteristics, and geologic conditions. Let's see soil properties. Soil properties means uniformly graded, fully saturated, cohesionless sandy soils are more prone to liquefaction than well-graded soil. Also, fine sands are more susceptible to liquefaction than coarse sand, gravelly soil, silt or clay. However, sands with some clay content can also liquefy. Similarly, loose sands have much higher tendency to liquefy than dense sands. Next is earthquake shaking characteristics. As shaking intensity increases, soil is subjected to higher stresses and strains and is more susceptible to liquefaction. Also, strong shaking with longer duration causes a large number of stress and strain cycles in soil, which also increases chances for liquefaction. Third is geologic conditions. Some geologic processes sort soils into uniform grain size and deposit them loosely. In geologic terms, some of these deposits are aeolian, fluvial, and colluvial deposits. Such soils are perfect candidates for liquefaction. Now let me explain you measures of liquefactions, how to overcome liquefaction. To overcome liquefactions, these three options can be adopted: increase liquefaction resistance of soil, reduce earthquake demand on soil, remove soil layers that can liquefy, or provide anchored pile foundation. Now let's understand them through this figure. As shown in figure 5a, increased liquefaction resistance of soil, that means densify loose deposits by vibrocompaction, impact compaction, and pressure grouting, or replace vulnerable soil by vibro replacement. Now let's see figure 5. Here, reduce earthquake demand on soil, that is, release the pore pressure by allowing drainage of water by stone columns, or increase confinement by adding surcharge. As you can see in figure 5c, remove soil layers that can liquefy, or use anchored piles as foundations going through liquefiable soil layers. This is all about earthquake tip number 31. You can download this earthquake tip from www.bmtpc.org. The next earthquake tip, which is the last tip, tip number 32, will be on why is quality critical in earthquake resistance buildings. Thank you.